Hi, I'm Jeff Groh and this is Calculus 1. Today we're going to talk about the tangent line approximation, and differentials. As you know from early on, the derivative gives you the slope of the tangent line. It's then easy to find the equation of the tangent line using the point slope form of a line. If you move the function value f of x naught over, the equation of the tangent line is equal to f of x naught plus f prime of x naught times the quantity x minus x naught. This is the tangent line. You can see then that if x is near x naught, then the value of the function at f is close to the value of the tangent line approximation, which means that f of x is approximately f of x naught plus f prime of x naught times x minus x naught. This is the tangent line approximation. I know what you're thinking. What good is this tangent line approximation? Let me give you an example that might help motivate why we would want to look at such a thing. Imagine that it's 1905 and you're the young Albert Einstein who has just come up with the following formula for the relativistic mass. Here, m naught is the rest mass of an object, v is its relative velocity to u, and c is the speed of light. So v divided by c is a fraction of the speed of light. We're going to square this. We're going to assume that you're moving slower than the speed of light, so this will be a fraction between 0 and 1. And so this subtraction here will give you something positive under the square root. Notice, however, that if v is equal to 0, the mass of the object is equal to the rest mass. As v gets closer and closer to the speed of light, this ratio gets closer and closer to 1, which makes the denominator closer and closer to 0, which means very, very small. You can see that in the limit, as v tends to the speed of light, the relativistic mass approaches infinity. What does this formula mean? This formula tells you that if an object is moving relative to you, it gets heavier in the sense of more mass. You should be aware that this formula is empirically true. Back in the early days of the cyclotron, people were accelerating electrons to very, very high fractions of the speed of light. They noticed that if they did not take into account that increased mass and hence increased momentum, then the magnet strength may not be designed strong enough and the electrons would start hitting the edges of the container. Now, we're going to play with this a little bit in the following way. We're going to rewrite it as rest mass equals relativistic mass times 1 minus v over c squared. And then I'm going to define the function f of x is the square root of 1 minus x. I want to find the tangent line approximation about x naught equals 0. First, note that f of 0 is the square root of 1 minus 0, which is 1. Then, let's calculate the derivative. The derivative of square root is 1 over 2 root, but you need to multiply by the derivative of the inside, which is negative 1. Then, if we evaluate that at 0, we'll have negative 1/2. It follows, then, that the square root of 1 minus x is approximately 1 minus 1/2 times x minus 0, which is 1 minus 1/2 x. So you're Einstein, and you have nothing better to do than to play around with this formula, since you're a clerk at the Swiss Patent Office. And so you come up with this expression, but in particular, you find that m naught is equal to m times 1 minus approximately equal to 1 minus 1/2 v over c squared. And so we'll play with this formula a little more. Distributing the m, we'll have 1/2 m v squared over c squared. Let's move some terms around. Let's move this term over there and this term over here. M minus m naught is the change, the difference between the rest mass and the relativistic mass. Let's denote that by delta m. Multiplying both sides by c squared, we have 1/2 mv squared is delta m times c squared. Those of you who have had some physics might recognize this as the kinetic energy. And so we've just shown that the kinetic energy is equal to the change in the mass times the speed of light squared. You might recognize this formula because it has some repute. So you can see these linearizations might give us important insights. As another example, let's find the tangent line approximation to the function f of x equals sine of x at x naught equals 0. To do this, first let's calculate f of 0. What's the sine of 0? As you'll recall, the sine function looks like this. And so it goes right through the origin. When x is 0, y is 0. The derivative of sine is cosine, and the derivative evaluated at 0 is cosine of 0, which is 1. It follows then that sine of x is approximately 0 plus 1 times x. In other words, the tangent line approximation at the origin is the line y equals x. When x is close to the origin for small values of x, the sine function is approximately x itself. That might help you explain this limit as x goes to 0. We spent a long time proving that this limit is equal to 1, but you can see now another reason why this should be true. As x gets small, close to 0, sine x and x are approximately the same, and so you get a limit of 1. We're now going to move on to the study of differentials. Recall from the mean value theorem if a function is continuous on a closed interval AB and differentiable on an open interval AB, then there's some point C between A and B where the slope of the tangent line is equal to the slope of the secant line. We're going to denote b minus a as delta x. That's a change in the x value. And f of b minus f of a is going to be delta y. That's the change in the y value. So here we'll have delta y over delta x. Normally we have to take the limit as delta x goes to 0 in order to obtain a derivative, but the mean value theorem guarantees the existence of some point in between a and b where the slope of the tangent line is equal to the slope of the secant line. Generally, if delta x is close to 0, then delta y over delta x is only approximately f prime of x. The mean value theorem guarantees some value of x equals c, that when you plug it in here you get equality. But generally you only get an approximation if delta x is close to 0. It follows then that the change in y is approximately f prime of x delta x. A small change in x can lead to a small change in y. That should make some kind of sense graphically. If you go from x naught to x, you have a small change in x. That leads to a small change in y. That's going to permit us to make the following definition. If dx is a real number, usually a small real number, and let's suppose y is equal to f of x, the differential of y is denoted by dy and defined by dy is f prime of x dx. The way to think about this differential dy is that that's a small change in y that results from a small change in x, or at least it's a good approximation to it. Here's an example. Suppose we have a photograph and it is 12 inches by 18 inches. However, suppose that these measurements are to within plus or minus 0.1 inch. The area should be 12 times 18 square inches. That's 216 square inches. However, we could incur some small error in these measurements. After all, every measurement is only good to within the accuracy of the instrument that you're using to make that measurement. A fundamental property of measurement is measurement error, and this must be acknowledged by all scientists and engineers. So, how good is this area calculation? The area formula generally is x times y. way to calculate the differential in this case is dx times y plus x times dy, i.e. use the product rule. It follows then that an estimate for the error in the area calculation is equal to the error in the x, which was 0.1, times y, which is 18, plus x, which was 12, times the error in y, which was 0.1. 18 and 12 makes what? 30 times 0.1. This is going to be 3 square inches. That 1/10 of an inch each way on the 2 dimensions of this rectangle can result in up to 3 square inches of error in the area computation. So instead of 216 square inches, it's 216 plus or minus 3 square inches. You can see that we kind of think of these differentials as a way of estimating errors that result from measurements whenever we're using these measurements to calculate some other variable. Let's suppose that we have y equals x squared, x equals 1, dx is 0.001. I want to find both dy and delta y to compare these two versions of the error that results from a small perturbation in x. First of all, dy is going to be derivative times dx. If x is 1 and dx is 0.001, dy is 0.002. Delta y should be f of 1.001 minus f of 1. Now this thing is squared, so this will just give us 1 squared, or 1. This first term, though, is 1.001 squared. Crunching this on my calculator, I get 0.002001. This is pretty close to the actual error that is incurred by going from 1 to 1.001. Pretty close. For example, suppose that a ball bearing has a radius of 0.5 centimeters plus or minus 0.01 centimeters. Estimate the error in the volume. To solve this problem, we need to know that the volume formula for a ball is 4/3 pi r cubed. It follows then that the error in the volume will be the derivative times the differential in r. The derivative is 4 pi r squared times that differential in r. Remember that dy is f prime of x dx. It follows then that if r is 0.5 and dr is 0.01, my calculator gives me an estimate on the error in the volume as 0.0314. Well, did we really need a calculator to do this? 1/2 squared is 1/4 times 4 cancels. We have pi divided by 100. Yeah. And this will be in cubic centimeters. Another use of the tangent line approximation is as follows. Estimate the square root of 16.5 using either the tangent line approximation or differentials. You can do it either way. Remember that the tangent line approximation is this. We'll choose x naught to be 16 because the square root of 16 is easy to calculate. In this case, x will be 16.5, so that the difference will be 0.5. So the square root of 16.5 is approximately the square root of 16. The derivative is 1 over 2 times the square root, evaluated at the point in question, and then the difference between these two numbers is 0.5. It follows then that the square root of 16.5 is approximately 4 plus square root of 16 is 4 again, but it's times 2, so it's going to be 1/8 times this 1/2. Crunching these numbers on my calculator, I get 4.0625. More accurately, the square root of 16.5 is 4.0620192202, according to my calculator. You can see that we're close. We're off in that 4th decimal place, which is pretty good. We're going to define different kinds of errors. dy is just the error in y. This is the absolute error. However, if we take dy divided by y, we get what is called the relative error. Think of the relative error in this way. If I launch a rocket and I miss the target by 100 feet, is that good or bad? Well, it depends. If I missed the target by 100 feet, but the object was on Mars, that's pretty good. That's a very small error. But then if I tell you, if I missed the target by 100 feet, but the target was 100 feet away, that's a very, very poor error. A very, very bad error. So the error itself doesn't tell you the whole story. The error divided by how big the quantity is gives you the relative error, and that's much more important in many circumstances. If I take that relative error and I multiply it by 100%, that's called the percent error. Then there are absolute versions of these. If I put the absolute value sign around each of these, I get the absolute relative error and the absolute percent error. Let me give you an example that I really like. Let's suppose that you have a little model rocket and it goes up, and from some distance you measure the angle of elevation when the rocket reaches apogee, its highest point above the surface of the Earth. Let's suppose that that's 65 degrees and that you are 200 feet away from the rocket when it is launched. Also suppose that the rocket goes straight up. I know that may not be your experience in launching rockets, but we're going to assume that here. We can deal with the drift as it goes up in Calculus 3. I have two questions. One, how high did the rocket go, if that's the height h? And two, find the maximum relative error if the angle measurement is to within, let's say, 3 degrees. One thing you should be wary of is the use of degrees in calculus. The derivative formulas only apply if the angles are measured in radians. So we're going to have to change this error to 3 pi over 180 radians. Calculating the height is pretty easy. We have an opposite side and an adjacent side. Opposite, adjacent. Which trig function are we talking about? That's right. The tangent of 65 degrees will be h divided by 200, and hence h is 200 times the tangent of 65 degrees. Crunching these numbers on my calculator and making sure that my calculator is in degree mode, since I'm using degrees right here, I'll have 200 times the tangent of 65 degrees. I'm getting 428.9, and this answer is in units of feet. That's all very nice. You could solve this problem in high school. It's a simple trigonometry problem. How high did the rocket go? But a more important question is, what's the maximum relative error? To calculate the relative error, we need to make theta a variable. And then estimate the error in h that results from an error in theta. The derivative is 200 secant squared theta, and then we multiply by d theta. The relative error in h is dh over h. Well, that's 200 secant squared theta d theta divided by 200 tangent theta. Notice that the 200s cancel. Let's play with this a little more. Secant is 1 over cosine, so we'll have cosine squared theta. Tangent is sine theta over cosine theta, and we still have this error in theta over here. One factor of cosine cancels, and we're left with sine theta times cosine theta in the denominator. Doesn't that almost look like a trigonometric identity to you? You might recall that the sine of 2 theta is 2. Sine theta, cosine theta. We almost have the double angle identity for sine in the denominator. What's missing is a factor of 2. I'm now ready to evaluate this and estimate our relative error. First, we have 2 divided by the sine of 2 times 65 degrees times 3 pi over 180 radians. Keep in mind, radians are the unitless unit. If this has units of feet and this has units of feet, the ratio should be unitless. Radians are unitless, and unitless ratios come out of sine functions. So the right side will be unitless as well. You can use degrees here because you can use whatever mode you want when calculating the sine function, but d theta must be in radians. The derivative formula that we used for tangent secant squared theta only applies if theta is measured in radians, so the error in theta must be in radians as well. This has to be not 3 degrees, but 3 pi over 180. Crunching these numbers, I get about 0.1367, i.e. almost 14%. We said earlier that h was 428.9 feet. It's kind of ridiculous using a decimal place here since we're up to 14% off. Using this relative error, we don't really know what h is. It's 428.9, but plus or minus about 14%. How high or how low can that be? Crunching these numbers on my calculator, I estimate the height is somewhere between 370 and 490 feet. As you can see, these nice little answers that you get from your high school trigonometry can be better informed by calculating these errors that result from the errors in the measurement. Keep in mind, every experiment involves measurement errors, and these must be accounted for. There's one more thing I wish to do with this example, and it should make you a better scientist. Remember, the relative error was 2 divided by the sine of 2 theta times d theta. Let's suppose there's nothing you can do about the error in theta because you're stuck with the measurement device that you have. Is there some way to make this relative error smaller? We can minimize the relative error by making the denominator of this fraction a maximum. The maximum of the sine function is 1, and that occurs when the angle going in is 90 degrees. That means a theta value of 45 degrees would give us the smallest relative error in our height calculation. We've set the observation post at the wrong place. Our angle of elevation when the rocket was at apogee was 65 degrees. The best thing you can do is move the observation post to a point where the angle of elevation will be about 45 degrees when the rocket is at apogee. We need to move the observation point from 200 feet to about 430 feet, and we'll have better control on the error in the height calculation. Here's the way to think about this then. You perform the experiment. You realize you don't have an optimal setup. You change the setup and then run the experiments with the experimental situation at its optimal level to minimize those relative errors. The next section is on L'Hopital's rule. If you don't put the little caret over the top of the O, this is sometimes spelled L'Hopital's rule. This rule is named after the Marquis de L'Hopital, who published a calculus text in which this theorem first appears. The theorem, however, was not proved by the Marquis de L'Hopital. Instead, the Marquis de L'Hopital was a student of Bernoulli. Bernoulli taught L'Hopital calculus, and the Marquis paid Bernoulli for those lecture notes. When he was done taking the notes, the Marquis put them into a book and published the book. Because that was the first book in which what we're going to discuss today appeared, it became known as L'Hopital's rule, even though he was just the student of Bernoulli. The theorem goes like this. F and G are differentiable on a neighborhood of x equals a, and g prime of x is not 0 except at x equals a, and if both limit as x goes to a of f of x is 0 and the limit as x goes to a of g of x is 0, then the limit as x goes to a of f of x over g of x, keeping in mind both f of x and g of x go to 0 as x goes to a, so this is a 0 divided by 0 case. If you take the limit as x goes to a of f prime of x over g prime of x, you should know that this theorem applies both in the 0 over 0 case and the infinity over infinity case. Before proving this, let me give you an example. We already know that sine x over x tends to 1 as x tends to 0. L'Hopital's rule says take the same limit, but take the derivative of sine, that's cosine, and the derivative of x is 1. The cosine of 0 is 1, and so you end up with 1 divided by 1, or a limit value of just 1. It would have been very nice to have had L'Hopital's rule way back at the beginning of the course when we first proved this. Do you remember how we proved it? We used areas of sectors of circles and of triangles, and we used the squeeze theorem to set up a sequence of inequalities. It was hard work. L'Hopital's rule makes it very easy work. As with all new developments in our theory, we need to prove this. Let's look at the limit as x goes to a, f of x over g of x. Keep in mind, this is the same as the limit as x goes to a of f of x minus f of a over g of x minus g of a. Since the limits are both 0 as x tends to a for f and g, their function values must be equal to those limit values, 0, because we assume this function is differentiable in some neighborhood. Also, because it's differentiable, we can write this as f of x minus f of a over x minus a over g of x minus g of a over x minus a. You can see then, because both f and g are differentiable, that you're going to get f prime of a over g prime of a, and we'll call that the end of the proof. There are more general versions of this theorem. The price you pay for those more general theorems is a more complicated proof. Let's do an example. Suppose I'm calculating the limit as x goes to 0 of e to the x minus 1 minus x divided by x squared. The first thing we should check is whether or not this is a L'Hopital's rule case. L'Hopital's rule cases are only 0 over 0 or infinity over infinity. Either of those two cases are fine. If it's not one of those cases, L'Hopital's rule doesn't work. If you plug 0 into the denominator, we clearly have 0 in the denominator. In the numerator, e to the 0 is 1. 1 minus 1 is 0. Again, we're plugging in x equals 0. This is a 0 over 0 case. In the context of limits, you'll recall 0 over 0 means more work. The nice thing about L'Hopital's rule is that the additional work is pretty simple. The derivative of the numerator is e to the x, the derivative of 1 is 0, and the derivative of x is 1. The derivative of the denominator is 2x. I want you to note carefully that I am not using the quotient rule. I'm using f prime divided by g prime. That might take a little getting used to. Notice that if we plug in 0 now, e to the 0 is 1, 1 minus 1 is 0, we'll have 0 over 0 again. What do? You use L'Hopital's rule again. The derivative of the numerator is now just e to the x, and the derivative of the denominator is 2. In the limit as x goes to 0, you have 1/2. As another example, consider the limit as x goes to infinity of, say, 3x squared plus 2 over 5x squared plus 3x plus 4. As you can see, as x goes to infinity, both the numerator and denominator go to infinity. Also, from your prior knowledge, since the highest degree in numerator and denominator is the same, we take the ratio of the leading coefficients to find the value of the limit. The answer had better be 3/5. Let's make sure that that's consistent with L'Hopital's rule. As you can see, we're going to get 6x for the derivative of the numerator, and for the denominator, 10x plus 3. It's still in the form infinity over infinity, so we take L'Hopital's rule and apply it again. And our answer is 3/5, just as we expected. All those crazy limits that we did in Chapter 2 are made simple by L'Hopital's rule. You remember how we would have approached this problem in Chapter 2? We would have multiplied numerator and denominator by the conjugate of the numerator, and then did some simplification. Here, you can see that we get a 0 over 0 case, and so we'll apply L'Hopital's rule. The derivative of the denominator is simply 1. The derivative of square root is 1 over 2 root, multiplied by the derivative of the inside, which is 1. The derivative of 1 is 0. You can see now that as x goes to 0, the numerator is 1/2, the denominator is 1. The limit is simply 1/2. I know that you're mad at me for making you do all those horrible limits in Chapter 2 when you know that I knew there would be a better way coming in the future, L'Hopital's rule, but we had to do it. Let's try another. Let's take the limit as x goes to 0 from the right. If x goes to 0 from the right, the inside of the parentheses goes to 1, and the exponent goes to infinity. This is not a L'Hopital's rule case. However, it is an indeterminate case. There are many indeterminate cases. Infinity minus infinity is indeterminate. 0 times infinity is indeterminate. 1 to the infinity, 0 to the 0, 0 over 0, infinity over infinity. These are all indeterminate cases. And one more, infinity to the 0 is an indeterminate case. Only these two, 0 over 0 and infinity over infinity, are L'Hopital's rule cases. However, it is possible, sometimes, to convert non-L'Hopital's rule cases into L'Hopital's rule cases, and that will be the case. There's a standard trick that you need to be aware of. And that is e to the log. Why is that so powerful? It allows us to take this exponent and write it here instead. Keep in mind that limits pass through continuous functions, which means we can write this as e to the limit as x goes to 0 from the right. What's left over is ln of 1 plus x divided by x. Think about this limit here. As x goes to 0 from the right, we get natural log of 1 in the numerator. The natural log of 1 is 0. And we're divided by 0. We now have a L'Hopital's rule case up here in the exponent of this exponential function. This e to the log business is a trick that you need to be aware of. The derivative of log is 1 over, and the derivative of x is just 1. You can see now that in the limit as x goes to 0 from the right, in the exponent we get 1. So the answer is e. Let's try another. Suppose we're taking the limit as x goes to infinity of x minus the square root of x squared plus 4x. This is not a L'Hopital's rule case because this is an infinity minus infinity case. The question is, can we convert such a thing into a L'Hopital's rule case? And the answer has to be yes, or else I wouldn't have brought it up. Yes. We'll multiply this top and bottom by its conjugate. We'll have x minus the square root of x squared plus 4x times the quantity x plus the square root of x squared plus 4x all over x plus the square root of x squared plus 4x. Multiplying this out, we get the limit as x goes to infinity of x squared. We'll have a plus x times the square root and a minus x times the square root. The last and the inner products cancel. We'll have minus x squared plus 4x all over x plus the square root of x squared plus 4x. The x squareds go, and we end up with the limit as x goes to infinity of negative 4x over x plus the square root of x squared plus 4x. You can see now that as x goes to infinity, we'll get a negative infinity over positive infinity. It's still an infinity over infinity case. This is now a L'Hopital's rule. Applying L'Hopital's rule, the derivative of the numerator is just minus 4. In the denominator we have 1 plus the derivative of square root is 1 over 2 root. Leave the inside alone, but then you multiply by the derivative of the inside, which is 2x plus 4. If you factor out an x squared from here, the x squared can come out of the square root as just an x. Now, as x goes to infinity, this clearly goes to 0. This ratio will become 2 divided by 2, which is 1. And we'll get negative 4 divided by 1 plus 1. The limit is negative 2. Let's do one more example. Let's do the limit as x goes to 0 from the right of x to the x. Now I know that's 0 to the power 0, which is not a L'Hopital's rule case. However, 0 to the 0 is an indeterminate case. So how do we do this? So how do we convert the 0 to the 0 case into a L'Hopital's rule case? You already know the trick. The trick is e to the log. That's how you get access to these exponents that you can bring down. We'll have the limit as x goes to 0 from the right of e to the x ln of x. The limit can be pushed up into the exponent, and you'll end up with a 0 times, what does the natural log go to as x goes to 0 from the right? Doesn't the natural log function look like this? So as you go to 0 from the right, the value will be minus infinity. This is a 0 times infinity case, which is still not a L'Hopital's rule case, but we're getting closer. We write e to the limit as x goes to 0 from the right of ln of x over 1 over x. You flip these down. Now as x goes to 0 from the right, the top goes to minus infinity, the bottom goes to plus infinity. We're now in an infinity over infinity case. It's a L'Hopital's rule case. So this will be e to the limit as x goes to 0 from the right. The derivative of ln of x is 1 over x. And the derivative of 1 over x is negative 1 over x squared. Rewriting this, we have e to the limit as x goes to 0 from the right. We'll invert and multiply and cancel. We'll end up with just minus x. As x goes to 0, we end up with e to the 0, and the limit is 1. As a final topic in this section, we're going to look at function growth rates. A lot of functions tend to infinity as x tends to infinity. The question is, which functions will tend to infinity faster? Many of these you know the answer to already. If I have x versus e to the x, which function grows faster? Well, obviously e to the x grows faster. But you can tell that by looking at the limit. If this limit ends up being 0, then e to the x grows to infinity much faster, way faster than y equals x. So much faster that this fraction gets driven to 0. And you can see that's true by L'Hopital's rule. Because this limit is 0, we deduce that e to the x grows faster than x. Using a similar method, it's easy to show that exponential growth, with any base, is faster than polynomial growth of any degree. Let's look at another example. Let's look at natural log of x divided by x squared. Who grows faster? Well, just given the graphs, you know x squared grows faster. But we can apply L'Hopital's rule to this. The derivative of ln of x is 1 over x, and the derivative of x squared is 2x. So simplifying this, we have the limit as x goes to infinity of 1 over 2x squared, and that's 0, so the bottom wins, the race to infinity. Note that if we had written the limit as x goes to infinity of x squared over ln of x, we would have found that the limit is equal to infinity. That just says the top wins the race to infinity, and again, x squared wins. There's one more topic in this entire chapter, and that's called Newton's method, or sometimes Newton's method of successive approximations. It works like this. Suppose that I would like to know where some function crosses the x-axis. I'm looking for its x-intercepts, its roots. Suppose that to begin with, I have no clue where to look, so I'm just going to close my eyes and mark off some spot. I'm going to call that spot here on the x-axis x0. Now, wherever I randomly chose that point is probably not going to be a root. But maybe I can take that one point on the curve and follow the slopes down closer to a root. Still not a root, but closer. And then I'll follow the tangent line at this point and get closer still. This is going to be much faster than the bisection method that we introduced earlier. Let's develop this method. First, let's write down the equation of the tangent line. The tangent line, you'll recall, was y minus f of x naught equals f prime of x naught times x minus x naught. This point is x naught f of x naught. The new point, x1, is going to be where this line crosses the x-axis. Y is going to be 0 when x is going to be x1. This is the only unknown in this equation. We can solve this equation for the unknown point x1, which is going to be our new best guess. Solving for x1, you get x naught minus f of x naught over f prime of x naught. We'll start with some random guess. This equation gives us a better guess. Similarly, xn plus 1 will be the old guess xn minus f of xn divided by f prime at xn. This is called Newton's method. As an example, suppose my function is x squared minus 2. I know where the roots are. The roots are plus or minus the square root of 2, and that's about 1.414. I know this already from the beginning, but we're going to apply Newton's method of successive approximations to estimate this. According to Newton's method, our new guesses are supposed to be equal to the old guesses times the function evaluated at xn divided by the derivative evaluated at xn. The function is xn squared minus 2, and the derivative is 2xn. Notice if we simplify this, we'll have xn, we'll have minus 1/2 xn, and when we distribute here, we'll get plus 1 divided by xn. We simplify this as xn plus 1 equals 1/2 xn plus 1 divided by xn. Let's suppose that the initial guess is 1, not 1.414. We could be more accurate, but let's just make a crude guess of this root equal to 1. The next guess, according to the formula, is going to be 1/2 plus 1 over 1, or 1.5. That's quite a bit better than our initial guess of only 1. Each time we apply a method that gets repeated over and over, we call that one iteration of the method. So far, after one iteration of Newton's method, we've gone from x equals 1 as a guess to the square root of 2 to 1.5. The next iteration of the method tells you to take 1/2 of the previous value plus 1 divided by the previous value. My calculator tells me that this is 1.4166 and so on. That's significantly better than 1 or even 1.5. Remember, the square root of 2, which is the value that we are approximating, is 1.414213562. How many iterations of the method will it take for me to get all of these digits? What I'll do is I'll store this value in my memory with all of these extra digits, and I'll plug it into this formula again for a third iteration of the method. Keeping in mind that so far we have 3 decimal place accuracy. I've stored this value in my calculator's memory. x3 is going to be 1/2 x2 plus 1 over x2. Now, according to my calculator, that's 1.414215,686. Before, we had 2 decimal place accuracy. Now, we're accurate to 5 decimal places. I'll store this value in memory, and we'll try a fourth iteration of the method. x4 will be 1/2 x3 plus 1 over x3. My calculator gives me 1.414213562. I'm now at the maximum level of accuracy of my handheld calculator. To get better accuracy, I'd have to use a different device. One thing you should take note of is that this method seems to accelerate in towards those answers that the bisection method did not do. The bisection method would take thousands of iterations to achieve this accuracy, where here it took 4 iterations of Newton's method to achieve the maximum accuracy of this handheld calculator. Now, there could be some problems that arise with respect to Newton's method. It's possible for Newton's method to oscillate back and forth as though you're getting closer to something, but there may not be anything. It's also possible for Newton's method to shoot you way off into oblivion here and to converge at nothing. The nice thing about the bisection method is that the intermediate value theorem implies that it will always work, whereas Newton's method won't always work. However, when Newton's method does work, it usually works a lot better than the bisection method, as you've just seen. I should give you one little cautionary note about the use of Newton's method. When I was taking college chemistry, way back when I was an undergraduate, in my chemistry lab we were required to solve this cubic equation that I couldn't remember for the life of me the trick that we were supposed to use. And so I figured I would just use Newton's method to find the roots of this cubic polynomial. Well, my answer was definitely a very good answer, but my lab TA didn't understand what I was doing, and so she gave me no credit. Despite the fact that my approximation technique, Newton's method, was better than what everyone else was doing, which they were just ignoring a term with a small coefficient, my answers were better, but my lab TA didn't understand what I was doing, and so she gave me no credit. That will sometimes happen.